So in this second episode, we're going to consider more thoroughly linear regression approach for solving supervised learning problems. So we consider analytical solution to building a regression model, then a more empirical approach and more computationally efficient one, and we go on with exploration of those models. So first of all, why do we want to study linear models? And in a nutshell, it is a combination of the input features that approximates our target quantities. So in this one-dimensional example of a regression model, we have this set of objects. We have the space X, and those objects are represented by blue dots here. And a regression model is a straight line, which is just some coefficient over X and Bayes term that shifts the line a little bit. And the model itself is a line, of course. And for classification problem, we can also have a very intuitive interpretation of the linear model. And the X features are here represented by two axes, X1 and X2. And the target that we want to predict is the color of every point. And since we target building a linear model, we would have some kind of linear boundary that separates points of different colors. So for linear model, it is essentially the case when the output is a linear combination of the inputs. Although it sounds a little bit naive, and it might be difficult to separate with linear combination features the problem depicted on the left, but if we find a way to transform the features, we can go from 2-dimension to third dimension and or look at a little bit differently at what we have, and then we can still draw the separation boundary here that would almost ideally classify orange and blue dots. So in this case, we added one more feature, which is equal to x1 squared plus x2 squared. And you see, if we look at these settings through the perspective of this feature, the orange and blue points become perfectly separable. So here is the illustration of a projection of two new features. And also, linear models are quite extensively used because it is the essential building block for many neural network architectures. And complicated modern architectures, you have an interconnection or interweaving between a linear model and some nonlinear activation functions. We'll talk about this in more details on the forthcoming lectures, but just for the record that linear models are not as trivial as those seem. So let's take a look at linear regression in particular. So we have our dots, our data set, blue dots, two features, x2, x1, and a target. And we want to minimize, as we mentioned in the previous episode, so-called loss function, which characterize how poor approximation of given model is. And in case of linear regression, the model that we target can be expressed as a vector theta multiplied by a vector of features. Of course, there could be a bias term as well, but for simplicity sake, we omit it for the moment. So, what kind of loss function can be used for building linear regression? We saw that mean squared error is one of the examples. Also, it could be mean absolute error. So instead of squared function, we have just module of the difference between prediction and the ground truth. And the benefit of using this function, despite it is not differentiable at a single point, it behaves much better with respect to outliers, to the points that sit far away from the central mass of your points, and due to this square second power in the mean squared error loss function, they may give a very significant term that would shift the solution of the regression away from the central and physical quantity. So this might, the second mean absolute error might be a more appropriate when you have outliers, noticeable and unwanted outliers. Also, there is a mean absolute percentage error, which looks at the relative error. So if in case you're interested in not in absolute values but in relative to the magnitude of y, so it goes a little smoother. And also there is a mean squared logarithmic error, and you see on the right how those two functions look like. And those functions are actually is the expression of our intuition of the data distribution that we have, distribution of the features, distribution of the labels and their relations. So in the trivial case, well, in case we have enough computation power, we can find analytical solution to regression problems. So if we write a design matrix where we have all the items of the data set written as rows, and every column is a feature in such a matrix, then we can rewrite MSE loss in a matrix form. So it can be expressed like this. So we subtract the prediction, and there's just a multiplication of this design matrix by vector of our thetas and vector of targets from vector of targets, and we just take an average. And analytically, we can solve this by requiring this loss equal to minimum, and it means that the derivative or gradient of this loss equals to 0. And also we want the second derivative become larger than 0. And so working on the first derivative, we can find the solution, which is depicted here. So it's just a simple linear algebra exercise. And here we just need to make a note that the matrix X should be invertible to be computable. for solution to be computable automatically, analytically. So, and also we need to take into account the second derivative. So when we write the second derivative, it is equal to this short. So it's true when all features or columns of the design matrix are linearly independent. And by the way, this condition also makes our matrix X transposed X invertible. And in case you have a correlation of your features, it is really unwanted property of the regression model. So in case you have no correlation, the distribution of thetas in your matrix would look like this. I mean, distribution, the loss function look like this along the optimum. And if there is a 50% correlation, the minimum region becomes quite extended in along the diagonal here. And if you have 100% correlation, you have solution like this. And it actually produces infinitely large number of possible solutions. Well, in the previous example, we omitted the bias term of the regression, so we considered only this part of the regression. But in the full term, we have to add a bias term. But actually, it doesn't imply any recalculation of the analytical solution, because we can just add a constant feature to a design matrix. So we go from here to here, and we just added this thing, and then we add this theta 0 to a theta matrix, and we come back to the original solution. And here is the illustration what we can lose without adding this theta 0 term. So without it, all the linear models should intersect the origin of coordinates point. So it should go from 0 somewhere else. And in case of theta 0, it would be equal to the distance from the 0 to the intersection of the line that we have as a solution. Although analytical solutions are nice and promising, when you want to compute it for a large data set, it might be rather computationally intensive. And to mitigate this problem, people use so-called gradient-based approach. So just a reminder, a gradient is a vector that consists of the components that are derivatives or partial derivatives of the function with respect to given coordinates. And such vector points towards the steepest function increase. So you see, if you see the function on this picture, and x here is the horizontal plane, x in the coordinates x1 and x2. So every point in this plane has a vector can be assigned to it, and this vector points to the increase of this function. And this is basically it. So if you want to find a minimum, you just want to follow the opposite direction. So in this, where the gradient descent optimization comes from. So we can optimize a function starting at some initial point and moving in the direction opposite to the gradient. So for every iteration k, we pick the previous value of xk and make a step in the opposite direction of the gradient, where alpha is a coefficient that just says how big the step should be in this direction. And it is called a learning rate. So for smooth convex function with a single minimum, we have a mathematically proven statement that the accuracy of such gradient descent approach equals to O1 over k, where k is number of iterations. And here is the illustration how it works, starting from initial position and eventually converging to a target. For non-convex function, things become a little more fancier because first of all, we may get to a minimum which is not global, and also we have a dependence on the starting point. So if we start from here, we get here. If we start from here, we get to completely different place here. Issue with the gradient is that it might also be computationally intensive in case you have a large number of objects, because you have to compute the loss function with respect to every object in your data and average all the values. To mitigate this complication, we may find an alternative if we compute the gradient not for all elements in our sample, but we can pick k elements at random at every optimization step. So we optimize it only for I beg pardon, for every step k, we pick lk elements at random. And it could be a constant, or it could be a number that changes over the gradient descent procedure. And then we compute the weights of our matrix by just subtracting gradient term from the previous step that is computed over those lk elements. It still converges, although the speed of convergence is a bit slower. So the mathematically proven fact that for convex and smooth function, the error of approximation is equal to 1 over square root of k. And it can be proved by batching or momentum or other tricks. Yeah, and here is the illustration that stochastic gradient descent goes actually a bit randomly, which is natural because you look not at the full gradient direction, but you look at the just partially computed direction. But then eventually it goes to the same place. One important note about the regression applicability of regression, as we saw in the example at the beginning of this episode, that if you add more complicated features, you can solve much more complicated problems. So, for example, if you add so-called feature transformation with any function phi and replace your initial features with those phi features, that so it operates on all the features that you have, and then you transform to a vector of the phi something features. Then you can make your solution much more powerful. And finding such function f phi is called feature engineering. And usually people do this when they have some intuition of the physical process that has generated the data, so you can understand what underlying properties of your features can result in the better approximation properties of your general model. So imagine you have dependency like this. So you have x plus x1 over 2 of x squared. So no matter what coefficient you add to x, you would not be able to approximate it smoothly. But if you add another feature, like x squared, then you can estimate the solution as a linear combination of x and x squared, and then it starts working much better. So in general, you can think of just adding polynomial features of degree p to original set of features. So we can introduce all unique multiplicative combinations of the following form. So x I to the power xk1 to the power of p1, k2 to the power of p2, etc., such that sum of those powers is less than the hyperparameter p. So for the original features, 3 original features and the degree of 3, we may end up with that number of features. So it brings us to a conclusion. So we looked at the linear models and we saw it is quite broadly used, and it underlines more complicated learning algorithms. And we looked how this problem can be solved from analytical point of view. And we looked how the stability of the solution depends on the feature correlation, which can be addressed in a proper way. And we looked how the linear models can be optimized with the gradient descent, or its more computationally friendly alternative stochastic descent. And feature transformation as a method that allows to add more power to those linear models. So a small chunk for food of thought is the question: how does polynomial feature expansion affect the complexity of the model? And one more question for yourself to check your understanding of things that you've learned in this episode. See you in the next episode.